Okay, it is a pleasure to introduce the first speaker of this afternoon session, who is Laurent Merseman from the Université d'Angers. And he's going to speak about the geography of Teichmuller spaces, stacks, sorry.
Thank you, and thanks to the organizer for this beautiful conference. I think I first met Pepe, but perhaps I'm wrong, in 95 or 96 in Lille. At that time, I was master student of Alberto, and you were visiting him in Lille. And I perfectly remember being in the office of Alberto with, and you explained me the basics of Chern classes. Do you remember this? Yeah, that's a nice memory for me. And well, since then, Pepe has played and continued to play a very important role in my mathematical and personal life, as well as Santiago and Mexico, and Santiago and Alberto. Of course, Mexico is very special for me, but everybody knows that. So I will talk of something else. In any case, I am very happy and very honored to be here, and I really wanted to be here. And let me also add some word on the Mexican-French CNRS laboratory, La Sol. Most of us knows the importance of this structure, and it's important to recall that without the energy and the determination of Pepe, this would never have been created. So he makes this possible, and that's really a great thing. So, por todo eso, gracias Pepe, y feliz cumpleaños. No me acuerdo exactamente qué número, pero eso lo podemos discutir después. Exactamente, sí. Okay. Latnek? Oh, okay. Okay. Okay, going back to the talk, I will talk about moduli problems in complex analytic geometry. So the setting here is the following. You fix some smooth, compact manifold M or connected, oriented, and sorry? And you are interested in the set of complex structure on M. So if you prefer, it's the moduli space of complex structure on M. So as I said, it's just the set of compact complex manifold, sorry. Which are diffeomorphic to M. And of course, this is much too big, so you divide by biholomorphism. Okay. But in fact, in this talk, I will take the Teichmuller variant. So I will focus on the Teichmuller variant. I will call it T of M. So it's exactly the same thing, but you divide by biholomorphism, smoothly isotopic, infinity isotopic to the identity. So if you want, that means that your compact complex manifold come with a marking, a smooth marking, and you don't identify every pair of isomorphic manifold, but when you have two isomorphic, complex isomorphic X and X prime, you identify them only in the marking. When you do this commutative diagram, you obtain here some map which is smoothly isotopic to the identity. So the reason for doing that will become clear in the sequel, is that it's simpler. But I will come back to that. Also, I want to emphasize that I am in full generality. I mean that the dimension here is arbitrary. I am not talking of this beautiful Teichmüller theory of surfaces. That's not my subject. And the compact complex manifold I use are any compact complex manifold, projective ones, scalar ones, but also non-scalar ones. So of course this is just a set, so this is not really interesting if you don't put analytic structure on it. If M is a surface, then it's a nice manifold, a nice complex manifold. This is also true in higher dimension for special types of complex structure. For example, for hyperscalar ones, you have nice Teichmüller spaces that are nice complex manifold. Well, non-Hausdorff, but nice. This is by the work of Verbitsky. But in general, this thing is not a complex manifold. No. And if you really want to work in this degree of generality, you need to use more sophisticated theory and see TM as an analytic stack. So I prove in 2019 that this is a bona fide analytic stack, at least as dimension of the automorphism group of involved complex manifolds is bounded. So as soon as for all x in Tm, so the dimension of the automorphism group is bounded by a universal constant. But this is a technical point. This is not very important. Yes. Yes. Yes, I will try. Yes. That's better? Okay. So for the moment, just think of that as saying that on this, where is it? On this space set, every point has a local analytic chart, but it may be a chart of manifolds or analytic space of orbifold, but it may also be something wilder. So let me make the difference between x is a good point of Teichmüller stack if you have a local chart at x, which is modeled on a manifold, complex manifold, or bifold, of a singular version. Okay. And otherwise, well, it's a breadpoint. So you still have some chart at a breadpoint, but you may think of something like an analytic space divided by the action of a Lie group that fixes x, or you have even worse thing that can appear. So now, this question of geography of a Teichmüller stack is to understand where are located the bad points. So ideally, you would like to say, okay, there are bad points, this cannot be avoided, but at least there exists the Zariski open substack. This is a well-defined notion in stack theory. So there is a well-defined open, there is a Zariski open substack formed only by good points. So that would be a very nice result, saying that, okay, the bad points, you control the bad points. I guess, yes. 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 For the observable surface, that is, yes. For S2 cross S2, that's not true. Yeah, but I mean, it's really a wild restriction because you can do a sort of, you can bound this dimension and take greater and greater stacks. And then if you don't have this condition, your object is a sort of direct limit of stacks. So I guess there are some technology to deal with that, but as far as I know, it's not a stack. Okay, so this question of geography is really the question of where are the bad points. And of course, are they concentrated in a strict analytic? So before giving some answers on this question, I will be a bit more precise about what means analytic stack. That will allow me to reformulate a bit this question. Then I will give you a conjecture, because I must say that although I'm obsessed with this problem for a long time, I have only partial answers. But I will give a very optimistic conjecture, and then I will give you some statements I am able to prove, or I think I am able to prove. Let's say like that. Okay. So, any questions so far? No? That's okay? For the setting and everything? Okay, so the philosophy of stack here is just that you want to put an analytic structure on this T of M in such a way that it allows you to recover all the families of complex manifolds diffeomorphic to M. So let me write this. So we want an analytic structure on Tm that contains all the information needed to construct what I will call M families. What is the M family? This is just, you take two analytic spaces, X and B, analytic map. You assume that P is smooth and proper. So smooth in the analytic sense, so you can think of this as being a submersion if B has no singularity. Then in that situation, all the fibers, so assume that B is connected, all the fibers are diffeomorphic. They are all compact complex manifold. So they are complex manifold because P is smooth. They are compact because it's proper. So compact complex manifold, they are all diffeomorphic by Ehresmann lemma. And of course, the M means that you want the fibers to be diffeomorphic to the fixed M. Okay? So you want to be able to construct all these families, plus all the morphisms, which I will call the M morphisms of family. Okay, so things like that. So how do you do that? Well, you reverse everything, and you define Tm. I will use the same notation. Perhaps it's not a good idea, but let's say that I do that. So you define the Specht-Müller stack as being all the M families over any analytic basis and all the M morphisms. You put this with a nice categorical structure. I won't discuss that. So you put, this is a nice category. By nice category, I mean that you have to check some points, okay? Of M families and M morphisms. And to have something which is closest to a moduli space. We are geometers, we want to see a moduli space, not to see a category of families of, okay? This comes with an analysis space, an atlas. This is very bad. Let me take this one. So this comes with atlas, with an analytic space. With a morphism to T of M. This is just by Lena's saying that your analytic space comes equipped with a M family. And of course, this family is special. From this family, from this family, you must be able to recover all the other families. All other families and morphisms are recovered from A, from this family. So that just means that you start with another M family, then you can decompose B, take an open covering of your base B, such that on every B alpha, this is obtained by pullback from this one. Okay? So you have some map F alpha in A, and this is isomorphic to the pullback. Okay. And then these local models, these local pullbacks are glue using pullbacks of local automorphism of your family. So if you know this atlas, if you are able to compute all the local automorphisms of your atlas, then you can reconstruct every. Okay. And there are some special sort of smoothness condition on this morphism. You have to think of this as a morphism, but I won't go into there. The important point is that you have the well-defined object is this category of M families, blah, blah, blah. And then you have a choice of an atlas, but it's not unique. It's like working on manifold. There are many atlases. They are all equivalent in a certain way. But when you want to do computation, if you want to have really a space on which you do computation, you choose an atlas.
You do get A, but some kind of a slice argument.
Sorry?
You do get A, some kind of a slice argument or something like that?
Oh, I will tell you. Yes, yes. So if you think of the theorem I quoted at the beginning, well, I said, but how does it work? How do you construct such a A? So we call you are in the general situation, so your manifolds are not always clear. So there is no period mapping, there is no Hodge theory. Oh, well. Perhaps there is some Hodge theory, but not enough Hodge theory to do something. One? Ah, two. Yes. Yes. Yes, I mean, it's not a formal definition. Okay. It's just an idea of. Yeah. It's even in that I didn't explain this. But okay. So some comments, if you want to prove this type of things, this is not so difficult. Yes. Yes. No, no. Here in this particular case, I'm just taking an open covering. Yes, Euclidean. Yes, I am in the analytic setting, so I'm not using some. Okay, but okay, it's a Grothendieck topology. Yes, that's true. But so comments. Indeed, this seems to be very, very difficult to find such a way, but in fact, you have a well-known theory that gives you a, which is Kodaira-Spencer theory. Kodaira-Spencer theory tells you that locally, you can always find some bigger family that determines all the other family. So as A, you can take, this is not the best choice, but you can just take a countable union of Kuranishi spaces from the Kodaira-Spencer theory. So I won't give any detail, but just want to say that Kodaira-Spencer theory gives you A with just okay, some reformulation, but gives you the first point. I mean, okay. And then what you really have to do is to check the smoothness conditions. This is about you have to control the local automorphism, and there is something to prove. Yeah. Yeah, you're right. I should say Kuranishi. Because locally, you can think of A as being a Kuranishi space. So that's, in a sense, this is a globalization of Kodaira-Spencer Kuranishi theory. Check the smoothness. Okay. So now, I can go back to this problem of points, good points, and the geography of a Teichmüller stack, because I will use an atlas. So start with M as before, and Tm. So assume that you have this condition on the dimension of your automorphism group. So you have a stack, analytic stack. Choose an atlas. And for simplicity, I will assume that R is reduced at every point. We call it a bona fide analytic space. Well, everybody which has done some computation in Kodaira-Spencer theory knows that the Kuranishi space may be not reduced, and that is a source of technical problems. So here I don't want to enter into that, so I assume that A is like that. So it's really a hypothesis. I cannot always ensure that there is an atlas like that. Okay. So you have your atlas. And it goes with a family. So each point is a complex manifold. Okay? And you have a family above. I didn't say, and this is not true, I didn't say that the same manifold is not encoded in several points of A. In general, the same X, you may have X and X prime inducing the same complex structure. You can even have some analytic subspace where all the xt here encode the same complex manifold as X. So this is not, I mean, this, you cannot directly have your local charts for T of M, the T of M as a set I defined at the beginning. From that, you have to take some quotient in some sense. Okay. So now what are the good points? Well, the good points are just the points where you can replace locally this atlas by an equivalent atlas. So you have perhaps a smaller one. So let's say that I do that. Perhaps a smaller one. such that when I take the family, so equivalent local atlas, so that in this family, two different fibers encode or are not isomorphic. So if you can do that, if you can replace locally your atlas by an atlas with really each point in the base is a different compact complex manifold, this really gives you the local chart on the set I was mentioning. And this is a good point because here this is supposed to be a manifold or an analytic space or I also accept our default. Okay. And so this is a good point. So I can find the good points on an atlas. The other are the bad points. Okay. Now, there is a way fact that goes back to the beginning of Kodaira-Spencer theory. Which is that the dimension, when you vary x in your atlas, in your stack, this dimension may jump. So it may vary from one point to another. So when you have a point such that in the neighborhood the dimension goes down, I call it a jumping point. And it's well known that jumping points are not good points. Okay, so they are. In fact, in that case, the best atlas you can obtain has this type of phenomenon that some of the manifolds close to your base point are encoded in a positive dimensional subspace. So this is bad. But the good news. Yeah, because it's a per semi-continuous function. So when you move, it can also only. So you have your point. You look by points.
Yes.
So here for then for the other complex manifold. Group. The I mentioned.
It's similarity, right?
Sorry.
So you have that it's such a similarity.
Yeah.
The structures.
Yeah.
You speak exactly about that.
Okay, so these are bad points, but forward. No, it may become more the situation may be more complicated. But it may happen that you have in a neighborhood all the other manifolds are biolomorphic. But it's one of the possible configurations. Okay. So that's a very bad phenomenon, but it's okay. We can say some more things about it. But the important point for us is that Grover proved that it happens on a strict analytic subspace of A. It only happens for jumping points from a strict analytic subspace of A. So from a point of view of geography, this is not so bad. Okay, they are located in something small. Now, I want to discuss.
And the jump in the cardinal of the working group, if all of them are finite, they are not for the
Sorry.
If all of the working groups are finite, but if all of them in the cardinal, it does not produce also that point?
Yes. Yes. Okay. Not always. When I talk of orbifold, it may be for things like that. But recall here that I am looking at the Teichmüller stack. So my automorphism group are the automorphism, the one I consider are the automorphisms that are smoothly isotopic to the identity. So this will avoid, especially in Keller setting, you avoid a lot of problems. But you have other problems. But we come back to this. Okay, so there is another phenomenon, more subtle, and this is the main phenomenon I want to focus on, which is the phenomenon of exceptional points. Okay, so if you have an exceptional point, what is an exceptional point? So assume it is not a jumping point. Okay, so you take something which is not a jumping point, and you assume that in A, you have here is X, and you have two sequence of points, let's say xn and x prime n, okay, with of course xn tends to x, well, okay, as a point, it tends to x, okay. The sequence of x prime n in A tends to x. They represent the same manifold, same complex manifold, up to biolomorphism, smoothly isotopic to the identity. But when you want to realize these isomorphisms, so you none of the realization, none of the sequence of morphism okay. Since they are isomorphic, I can choose an isomorphism between them. Of course, there are some choice because I can compose with an automorphism of xn if xn has some automorphism. So there are consequences like that. But the exceptional case is the case when none of these sequences converge, when n goes to infinity. So there's something is missing here in a sense. You would like this sequence of phi n to converge to a biolomorphism of a fiber x, to an automorphism of x. And it does not happen. And even if you renormalize with automorphism of the other points of xn, you don't have something that converge. Okay. So now I claim that all the geography, apart from jumping points, all the bad geography is located on exceptional points. So if you understand them and understand where they are, you're happy. The problem is that I don't understand. But let me state a conjecture. Sorry? Yes. Oh, and once again, we call that we are smoothly isotopic to the identity. This phenomenon is easy to produce if you are in the moduli stack. So more or less, everything I will say now is completely false if you replace the Teichmüller stack by the moduli stack. So this is the reason for using Teichmüller stack. Of the nearby fibers that does not converge. Yeah. Okay. Okay. I have to. Sorry, I have a few time to explain, but perhaps we can. Okay. Let me go on. So the conjecture is. There are two conjectures, in fact, because the main point is that situation is completely different if you are in the Keller setting or in the non-Keller setting. So to simplify, when I say I am in the Keller setting, let's say that all the complex manifolds in A correspond to Keller manifolds. And when I say that we are in a non-Keller setting, let's say that all the manifolds appearing are non-Keller. Of course, you can have some mixing, maybe. But, okay, let's think. So in the Keller case, this is an optimistic conjecture, okay, just to give you a hint. Well, I hope, I think, depends on the day, that there is no exceptional point. This does not exist. Once again, if you do this in the moduli stack, it's easy to find exceptional points. Complex tori of dimension 2 have exceptional points in the moduli stack, but not in the Keller stack. And in the non-Keller case, not only they exist, they may exist, but exceptional points may be dense, or at least locally. Of course, it's always very difficult to describe complete A. Okay, what's the difference? This is classical and easy to understand. When you look at the difference, I have a definition. Here I have sequence of biolomorphism. Of course, it's classical in complex analytic geometry. When you have that, you look at the graphs of the biolomorphism, and you see them as cycle in some cycle space, like the Douady or the Barley cycle space. And in the Keller case, you have compacity results. So as cycles, such this type of this type of sequences always converge as cycle, as singular cycle. So this compacity result makes it much more difficult to have something like that, especially because I am working with things smoothly isotopic to the identity. So the other problem in the point is that in general automorphism in the Keller category acts on cohomology or things like that, so they are not isotopic to the identity. But of course, this is not enough to prove that, or I'm not able to prove that just with that. But that explains the difference. Now, okay, you will be able to say something positive. Okay, difference, so is, okay.
What would be an example of how to get from Keller points like this?
I will try to go to that. Okay. Okay. Well, but okay, we will see. We call it a conjecture. Okay. So this is very nice because what it tells you is there is really a big difference. This difference, you cannot see this difference when you look at the moduli stack, because on the moduli stack you have a mapping class group. Mapping class group can act very widely on the Teichmüller stack, and all the nice property you have can be lost when passing to the moduli stack. Okay, but let's look at the two cases, Keller and non-Keller. In the Keller case, I cannot prove that there is no exceptional point, but at least I can prove that the closure of exceptional points is a strict analytic substack of A. So like jumping points, it's not so bad. If there exists an exceptional point, they are located on an analytic subspace. So you have the jumping point, and you have another strict analytic they may intersect, and this is the closure of exceptional points. Now, if you look at the other points, well, the other points are good points, are orbifold good points. The closure of exceptional points is a strict analytic subspace of A, or of your stack if you prefer. And the rest of the points, so when you remove jumping and this closure of exceptional points, other points are good points. Okay, I don't have time to comment. Let me rather say what I am able to do on the non-Keller case. Sorry. No, they may intersect. You can have a jumping.
You're saying that if it's not exceptional, it's also
Over points, okay, you have to remove also the jumping. Over points, not jumping and not in the closure. In the closure of exceptional points. Yes, sorry. So that's a very nice situation. In the non-Keller case, well, I am able to prove nothing. I don't have an example of exceptional point. So that's something very bad. And I don't have this. But if we slightly change the problem, I can prove this conjecture. So what is the change in the non-Keller case? I define the Teichmüller stack. Also, we have a moduli stack. But we can also put something a bit different, slightly different. Let's say what I consider what I will call T of M. As before, this is the compact complex manifold smoothly diffeomorphic to M. Okay? But this time I won't divide by biholomorphism smoothly isotopic to the identity, but by biholomorphism that induce the identity in cohomology. Of course, if you are isotopic to the identity, you induce the identity in cohomology, but this is, the converse is false. So if you replace your Teichmüller stack by this TZ Teichmüller stack, you may do exactly the same as before. This is an analytic stack. You may define a notion of the exceptional point, where of course this is exactly like this. Just here the phi n are not supposed to be smoothly isotopic to the identity, but just to induce the identity in cohomology. So if you do this slightly different version, then there are examples of non-Keller, there are examples with, there exists a threefold example with exceptional points, well, the exceptional points, okay. Locally dense in your atlas, and also with automorphism group that induce the identity in cohomology being infinite. What I didn't say is that the classical result, classical consequence of this stuff on cycle space and Barley and Lib. No, it's infinite. So this is not possible in the Keller case. So this, I like to think that this is a, but this tells you that we should, there should exist the same type of phenomenon when passing to the real Teichmüller stack and not to this T of Z. At least what is true is that this situation cannot happen in the Keller case. In the Keller case, you cannot have this automorphism group to be infinite, and you cannot have this, this local density. So, okay, I think I'm done.
Any questions, comments?
What happens with Hopf surfaces?
Oh, Hopf surfaces are really nice, but they don't have this, this type of exceptional points. In fact, in the case of Hopf surface, so your Teichmüller stack or a connected component of your Teichmüller stack is exactly is a bounded domain. You start with a bounded domain in C2. You're just given by the determinant and the trace, okay, of a linear part of a contraction of the surface. And then, so this is a bounded domain. Let's say that something like D star cross D. I don't remember exactly, but okay, it's the trace and the determinant of contracting matrix, which is okay. And but you have a countable number of analytic curves corresponding to the resonance. So on these curves, you have to think that you have to put 2 points and not 1. So if you want to do an atlas, this is not easy. Because of course, this description is a description really as a set or as a topological space. This is not Hausdorff. But you can construct some nice atlas, nice connected atlas. But in any case, these are jumping points, let's say. The other are good points. You have no exceptional points. Same thing.
Any more questions?
The point, the question is, what is definable in this construction? If you can have some definability. It's clear that if you consider this kind of equivalence relation, it's not definable. Yeah, but can you have sometimes a definable theory? For instance, what you describe for the Hopf surfaces, it looks very definable.
Yes, I guess that if you are in a definable category, and okay, perhaps things are very different. I don't know. Really, I don't know.
Because it's somehow it
right.
looks very natural to
yes.
use the minimal structures for this
Yes,
business,
you're right.
but
Any more questions, comments? And then let's thank the speaker again. We come back in 12 minutes.
Just a comment. No, tomorrow at 11:14, after the lecture of Guillermo Peñafort, we'll have a group photo here. Okay.
chaque fois
ça
qu'il-
marche, oui, ça a l'air
Chaque
de
fois que
marcher.
tu souffles dedans.
Ah, parce que ça-
Let's begin the last session of today. It's a pleasure to introduce Jean-Paul Bracelet from Aix-en-Marseille Université, and he's going to talk about Poincaré hop from the origin to the present day.
Is it okay? Yes, okay, good. Okay, so I think you are already very tired to had very nice lectures today, and so I will be very, very elementary. But I am quite sure there are things that I will tell you that you don't know, even from the very beginning of the story of Poincaré hop. Before Poincaré hop, you know already from people. I will invite you to a trip, and that trip will be in Europe, and it will begin in Greece, here, okay? Then we will go to Sicily, here. Going, maybe we will take the boat to Netherlands, and then to Stockholm, and then we will go to Germany, between France and Germany. So a nice trip, huh? In time. And the beginning is what you know very well. It's that you have cities here of Miletus. Miletus at that time, it was that time here. Miletus was on the boundary of the sea. There was a port. It was a port at that time. Now it's not anymore. The island, it's an island. Here there is a sea before. In between. Samos is an island in Greece. It's very curious because this is a boundary between Greece and Turkey, as you can see, going like that. So all these islands belong to Greece. And we will go to Athens. This is a beach on Samos. And in Samos, we meet two guys, Thales, more 20 at that time, and Pythagoras is more or less 20. I have to say that I have a good souvenir of Pythagoras, because when I was at second school, at 12, he was saying that Pythagoras was born in 500 before Christus. And I said to the professor, this is not possible. How can you ask Pythagoras, in what year did you born? And to say 570 years before Christus, it's not possible. So we have to think of that. Okay, and so Pythagoras was discovered the three first regular. Okay, so the tetrahedron, the hexahedron, which is the cube, and the octahedron. And then the two more, icosahedron and dodecahedron, was this guy, Theaetetus of Athens. He was working with his computer at that time. And he discovers the two last of the five, what we call Platonic polyhedra. But in fact, it's not at all Platon who discovered this. It is Pythagoras and Theaetetus of Athens. And Theaetetus of Athens was able to say that, and then it's finished. After these five, there is no more regular polyhedra. But this appears in Plato wrote this in his dialogue and so on. So it is, we call Platonic polyhedra. But this is not very good. as a, okay? This is Pythagoras and Theaetetus of 5 Platonic polyhedra. Plato is there, but writing. After that, you had Archimedes, who generalized with truncation of this already known polyhedra. Okay, and Archimedes is now in 250, we say, before Christus. And Archimedes was living in Sicily, which is here. So you have Sicily that we have seen before, and he was in Syracuse here. Sicily at that time was Greek, but after that Sicily was from Roman, Germanic, Ostrogoth, Byzantine, Muslim, Viking, Norman, Swabian, even from Angers. Where is Laurent? Here. So, the people of Angers was Sicily was from Angers, and then Valenciano. Where is Juanjo? Okay, so did you that time? So we are now in Christmas, 1530, and this is very important. We are in this city of Messine. Sorry, I did not say. We are now in Messine. Messine, there is the sea is before that. There is a gulf here, and so Messine on the beach here, and in Messine, we are in Messine in Christmas, 15 December, and we are with this monk, Italian monk, Francesco Maurolico. I think you don't know this guy. Because Francesco Maurolico was playing with this regular convex polyhedra, and he was trying to give all possible planar representation of this polyhedra, and looking at if they are isomorph or not, and giving the. Okay. So he was classifying as well this representation, planar representation of polyhedra, and I don't know if some people below 60 learned Latin.
We have to take models. In school, we have to take models and stuff.
Ah, yeah. So you speak Latin?
Yeah.
You speak Latin?
Yeah.
Yeah. And if people below 60, did you learn Latin? Nobody. Yes? Oh, good. You will translate. I will give you Latin now. So, in fact, it's only 10 years ago that Italian student working in more in history than in mathematics. She is more historian than mathematician. And in a PhD thesis, 10 years ago, she says the following. Exactly. 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 200 before Euler. It is clear, it is evident, each regular solid, the number of faces added to the number of vertices exceed by 2 the number of edges. V minus E plus F equal 2. The formula is Maurolico formula. 10 years ago, the student found this and this is written by Maurolico, Francesco Maurolico. No, for Platonic, where I say it's a Platonic solid. Maurolico was working on this Platonic solid only. Okay, so it's not. I don't say for all. So Maurolico already found the formula, only making this planar representation. So this is very important, I think, to know that. Of course, I will not ask to change all names in all books from Euler to Maurolico, but it's good to know that before Euler it was already known, and more that Maurolico does not say if he was knowing that from other people or if he discovered by himself. It says only it is evident that. But some people say that Archimedes already knowing the formula, but okay, but without any proof. But Maurolico there is a proof. Okay, good. So now we I said to you, we will travel now from, we came Greece, Sicily, now we go to Netherlands, and then we will go to Stockholm, here, Sweden. In Netherlands, we pass positive time after Christus. So Descartes is writing a theorem. It is unknown when Descartes wrote his theorem. But his theorem is saying that if you have a convex polyhedron, any convex polyhedron, the sum of the angle of all faces of the convex polyhedron is equal to 2v minus 2 pi, where v is the number of vertices. For example, here you count the sum of all these angles on these visible faces, but also on the faces which are not visible. Okay, and the sum of all these angles is equal to pi. This is Descartes' theorem. We will see that it was discovered later, but when did he wrote this theorem? I don't know. We don't know. And Descartes was invited by this woman here, which is a queen of Sweden, Christine. She is at that time she is 22. But she already had a good correspondence with Descartes during 3 years before. And she wanted to invite Descartes to discuss mathematics, astronomy, philosophy, religion, many things she wanted. So she invited Descartes, so you have here two representations of the meetings between Descartes and the Queen. And Descartes arrived in October 1649. But the Queen is like all queen and all kings. You have to wait before meeting. And so he had to wait until December 18. And Christine wanted to meet Descartes at 5 o'clock in the morning. It is winter. It is in Sweden. It's very cold. Okay? And so Descartes, and they were also discussing in the library of the castle, which is very, very cold. So Descartes got a pneumonia, and he died 2 months later. So Descartes died in Stockholm, in Sweden, 2 months after arriving in winter to discuss with the Queen. So, in fact, Descartes was hosted by the French ambassador in Stockholm, Pierre Chanu. And so all paper of Descartes were in Pierre Chanu's house, an apartment. And he sent all manuscripts to Paris. He was knowing Claude Clercellier, his brother-in-law, but Clercellier was editor. So he sent all manuscripts of Descartes in order to publish. And so, but arriving in Paris, there was a big boat from Stockholm to Rouen on the Seine, River Seine, and from Rouen to Paris, a small boat, and the boat, arriving in Paris, sank in the Seine with all Descartes manuscripts. After 3 days, the chest it was a wood chest, was recovered, and Clercellier tried to dry. He had no, I don't know, with this, that you put all clothes to dry. And so he asked also some people to help him, but there was a lot of letters from Descartes, and of people wanting sent to Descartes, and also many documents and so on. So they mixed everything. It was completely crazy. And so Clercellier tried to dry and to order. And then a little later, Leibniz, I didn't know that Leibniz had a role of copier, photocopier, I don't know in English, photocopy. He was making photocopy at that time. There was no photocopy at that time, but Leibniz was copying. And so he copied the Descartes manuscript, and also, it's very funny that at the same time, he had the manuscript from Pascal, the famous Pascal, some traité des coniques. And Leibniz copied also the Pascal traité des coniques. I know. this, well, I have no time to say everything, but that's true. That's true. And so Leibniz intended to publish the Descartes manuscript, but of course he did not add all the documents, all the manuscript of Descartes, because a lot of them were with a lot of water when the chest sank in the river. But Leibniz came to Hanover, in Germany. I said to you that we will go to Germany with a copy of the Descartes manuscript. He died without publishing the manuscript. So what happened? What happened? We will see later. Now we will go to. I will follow chronology. Oh. So the chronology now is with Euler. Euler is in Berlin, and he is trying to classify. He wanted to classify polyhedra, convex polyhedra. I don't know if it's true. People say that it is a legend. So the legend says that. The legend says that Euler was trying to classify. And for example, he was first taking classifying by number of faces. So you take 3, 4, 5, 6, etc. faces. And for hexaedra, which are polyhedra possible, with 6 faces. So you have, then he classified with the number of vertices. So it can be 5, 6, 7, 8 vertices, no more. Okay, when you have hexaedra with 6 faces. And then you see, Euler sees that there are 2 with 6 vertices, 2 with 7, and 2 with 8. So he wants to classify, he wants to distinguish both of them. So he said, why not, with a number of vertices? But here, he had 6 faces, 6 vertices, and he finds always 10 edges. And for the other, always 10 as well. So he said, both of them, strange, 10. And with 7 vertices, here are 11 edges and 11 edges. Strange. And for both with 8 vertices, he found 12 edges, both of them. So he said, strange, of course. And he made this not only for convex polyhedra with faces, but also for more faces, okay? And so finally, he has seen that there is this formula, the Euler formula, with all these examples, of course, that you have V minus E plus F equal to, that you have seen with Mauricio, but now it is with Euler. And he sent a letter to his friend, Goldbach. Yeah? After that. First of all, he sent a letter to his friend. I discovered the thing. Yeah, he was so happy that to discover the relation that he sent a letter on this day, 14 November, to his friend. The first thing is a letter. After that, the friend, his friend, Christian Goldbach, said to Euler, you have to publish. And Euler published it. There was a gap, and he published second time, again, but at that time, it was not known that there was a gap. The gap has been seen later on. But the proof Euler is not completely correct. There are some gaps. Okay, so he published, I said, to publish, but there is a gap. Sorry. So, in fact, now we will see that Descartes' theorem that we have seen before, with the number of the sum of all angles, is absolutely equivalent to Euler formula. So that is the reason for which some people say that Descartes discovered Euler formula, because it's absolutely equivalent. The two are equivalent. You can give that to your student. It's a very easy exercise, very interesting exercise, to prove equivalence in the both Descartes theorem and Euler formula. I continue to say Euler formula. I will not say Mauricio formula, but okay. So there is equivalence between both, and it's a good exercise to give to students at the beginning. Well, so I continue. So Descartes' manuscript was in Paris. Leibniz take a copy but the manuscript was in Paris, and it was completely lost. We don't know what happened. I remember to you that just before we have seen Euler formula, and then a French ambassador to Austria-Hungary came in a home of Hanover. Hanover was at that time in Austria. Hanover was at that time in Austria. French ambassador in Austria-Hungary came to how he was fan of Leibniz, so he came to Leibniz's house, and he discovered there was a lot of dust everywhere, and there were some manuscripts, a pile of manuscripts. Imagine if you let your office during 20 years, how will be your manuscript? And discovered within, under the ancient dust, he discovered the Descartes, at least what Leibniz copied from the Descartes manuscript. And then, Ernest de Fox de Jonquière, who was an academician, he published an auto-compte-rendu and tells the story in 1890. Okay, so this is... Patrick, I will give you the file. I will give you the file. I see that you... Okay, good. Okay, so now who published a proof of Euler formula? Because I said that Euler proof had a gap. In fact, later on, and it is well later because it's 2007 only, that Francese and Richardson, they used the Euler technique to give a proof of the Euler. And so now it's okay. And the gap is okay. And the first complete proof, in fact, was by Legendre. And Legendre was using a little of Descartes' way of working. But maybe you know better the combinatorial proof by Cauchy. Cauchy was a little later, but purely combinatorial. Maybe I will see if I have time, I will tell you a little. And the proof by Cauchy. But the proof by Cauchy is very nice. But two guys, Lakatos made, there is a book by Lakatos, I don't know if you know this book, we say that the proof by Cauchy is not, there is a gap also in the proof by Cauchy. And Elon Lima is a Brazilian professor, is very good, he made a very nice book, very, very nice, fantastic book. And, but human is, can make mistake. And Elon Lima says that it is impossible to prove Euler formula using Cauchy method. And this is not true, because with one of my former students, Nguyen Tibish, in 2020, we proved that it is possible to prove the Euler formula using the Cauchy method. And for that, we use these two instruments. On the left is a salad bowl that my grandmother was using to take water out of the salad. And you take this thing and you make like this. So the water is going. So it's more ecological than some things we had now for the salad. And on the Vietnamese side is a fisherman net. So you can pass the video, please. I need a change of the number 2, the video. Okay. And you will see how I used this. We use this salad bowl. The number 2. 2 is the video. Here is 3 and 4. Yeah, good. So, you see the salad bowl is on the plane, and then you take up, and then all the triangulation, which is planar triangulation, goes like a pyramid, but all the triangulation, all goes in the same time, growing as a pyramid. So, you know, you see that? that from the planar triangulation, you obtain a pyramidal triangulation. Okay? And this was what? Ah, yeah. Okay, so it's planar, and then up. So you take a triangle, any triangle inside, and you take everything. Everything will come. Okay? So we can put number 3. So no, this we have seen. I don't know how, but a video Beamer. Number 3, yeah, that one. Okay, perfect. So, take a convex polyhedra, any convex polyhedra. You choose one of the faces that will be the face horizontal, on the horizontal plane. Okay, you choose one of the faces, which is green, and you choose one simplex or cell or of your polyhedra, which is in fact, here is my picture is bad because I put parallel, but it can be any situation. Okay, okay. And so you choose one which is more or less opposite. It can be also that one, or even one with a common point. This is not a problem. So any which is opposite, and then you take a point of this, and you take. So this is the beginning of a Cauchy proof. Okay, and Cauchy takes stereographic projection of the polyhedra on the plane. So you can see very well that you project the polyhedra on the plane. You project, but of course this simplex or cell will not appear. It will be the exterior. Okay? So now you have a polyhedra here, which is a polygon, which is a planar polygon, with the same number of faces, edges, and vertex, less than this simplex, which that you have to count in the formula. Huh? The formula will be here. I will prefer to say n0, the number of vertices, n1, the number of faces, plus n2, the number of edges. Okay? So here, if you delete that one, sorry? Yeah? Yeah? It's not. Sorry. Yeah. Yeah, it was good here, but not here. Okay, thank you. This one was correct. Okay, thank you. Yeah. Okay, so now So now you are in a plane, but don't forget to take one element of n that you take out. Okay, so you are in the plane, and you have a plane in the plane like this. Okay, with the blue is the boundary of the simplex or cell that you disappear. And then what say Cauchy? Cauchy says, for example, when I have this, I can delete an edge and a triangle. So if I delete an edge and a triangle, I will have a new polygon like this, okay? And then if I delete a triangle, delete one here, so I don't change the formula. Okay, if you take one less here and here, the formula is the same. And then you make this for this triangle here. So now the new boundary will be here. And you make also the same for this one. So the new boundary will be here. And the formula is the same. But now you have this triangle. The boundary is like this, like this, like this, like this. Okay? So you have this triangle here. We have one vertex, two edges, and one face. So one vertex here, edges, and one face, the sum, 1 minus 2 plus 1, does not change. This is the Cauchy. way to prove the formula. The problem is that on my picture, it's very easy to see that, okay, it works. But when you have a complicated picture, Lakatos explains that you can go taking out, and at the end, you don't find, if you don't take care, it can be anything at the end. Okay? Not, in principle, if you do correctly, it will be a triangle. And Cauchy, for Cauchy, it was always a triangle, but not. And so, what we did, you take any simplex, any triangle inside, and you do the ball. Okay, so you take up from the plane, and then you obtain a pyramid like you had in. And then it's easy to see, and you can see by yourself. It's not difficult to see that you can go. Now you have a certain order, you will say, to process, and then it will be okay. Okay? This process, using Cauchy method, you record the formula without any problem. So, in fact, in time of Cauchy, people were happy having a polygon in the plane, and that's it. And they did not think that you can hop. And
You just try to prove the car version. And just
I did not try. Good idea.
notice that at every
Good.
vertex you have a full,
Very good. Very good.
full
Yeah,
circle
yeah.
and you fit.
Very good. Very good. Yeah, very good. Very good. You are right. You are right. Okay. So this is a proof of Euler formula using Cauchy method, and it is possible to prove Euler formula using Cauchy method. So now in history, I will go more faster because you know very well this. Okay, this you have now to. This you know very well. Here, maybe you don't know too much. We are now in 1880, and the time you have in Paris to look at things up and to look at things down. The Eiffel Tower is growing, and this is the first metro in Paris, the first metro line in Paris at that time. But the most important event is this one. Do you know? 22 May 1885. It's event in France, I think the event where there was more people, 2 million people. 2 million people. And maybe Poincaré is there somewhere. I did not succeed to recognize him. He's somewhere. And 2 million people. And this is, here, the coffin is Victor Hugo. It is a Victor Hugo. Victor Hugo did not want to be built with a car. He wanted to be with a horse carriage in Paris. And it was a long way, a long trip for the funeral. And all along, it was possible to rent places in apartment for the funeral of Victor. So very funny. So this is important because Victor had more people in funerals than Johnny Hallyday. Yeah. Yeah, Johnny Hallyday. You don't know this guy? No. Okay. Okay. So Poincaré, you know very well that Poincaré generalized the Euler characteristic, taking here plus so you know very well. Alternate sum. Sorry? Yeah, this is Poincaré. It's Henri. It's not.
Non, pas le président.
Pas le président. Non, c'est lui. Si, c'est lui. C'est lui. Je ne sais pas à quel âge. Hein. J'ai pris la photo comme ça. No, it's Poincaré. You will verify. Okay. You will tell me. Okay. So here's Poincaré, here's Hopf. And you know very well this formula, which is Poincaré-Hopf formula for compact manifold. Okay? So this is the formula. Poincaré proves in dimension and Hopf any dimension. Okay. So I will use the board so you can but here. I will go to singular varieties. So will go now to singular varieties. And this is the work of Marie-Hélène Schwartz. In notre compte rendu, 22 and 22/9 March. Thank you. Gracias. Oh. 65. I put 45 because for 22 March 45 is my birthday. So it's very funny that Marie-Hélène Schwartz published exactly the day. Yeah. My God. Thank you. Thank you. Thank you. So it's the reason for which I did not see with all the people. Okay. Okay. So Marie-Hélène Schwartz published a proof of Poincaré theorem for singular varieties. And for the moment, it's the only proof we know. What she did also in that publication to introduce characteristic classes for singular varieties, chain classes for singular varieties in the same publication. And of course, so you have chain classes by Marie-Hélène Schwartz in the same publication. So it is 1965. As you know, there was many people spoke already about Deligny Poincaré conjecture. Deligny Grothendieck, sorry. Deligny Grothendieck. Conjecture. 19. So this is difficult to say because 7, 8, something like that. Deligny and Grothendieck, they don't agree on that point. I asked Sullivan because Sullivan discussed with Deligny, but no more information. So more or less at that time, and the proof of Deligny Grothendieck conjecture in 1974 by Macpherson. In fact, this class is live in cohomology. If you have X singular variety analytic, here we are in real, so it can be semi-analytic, sub-analytic, semi-algebraic, sub-analytic, everything you know that has a stratification. Okay? So if X is singular and M is smooth, a manifold, so you have these cohomology groups. And by obstruction theory, you can construct classes in these cohomology groups. And Macpherson classes corresponding to the and Grothendieck conjecture are in homology of X. And in fact, there is here an isomorphism. And in 1970, I had better to know, this is more or less 4 years, 8. So Marie-Hélène Schwartz and myself, we proved that the by Macpherson are the same than the classes defined previously by Marie-Hélène Schwartz. And that I said always it's a unique example I have, I know in mathematics, where a conjecture by Deligny and Grothendieck is not nothing. The conjecture has been proved before, the conjecture. And I think this is the only example we have in mathematics. If you have another example, tell me. But so I have only 5 minutes. So, yeah, only 5 is exact, okay. So I have very few time. And just to say that, if you, first of all, you can think when you have a stratified variety with a strata, S1, S2, okay? And you can say, oh, if I want a Poincaré theorem, I have to take vector fields. But vector field, you cannot take a vector field which is anything here, because you cannot compute. To compute the index of a vector field, you need to be in a manifold, because you will take a ball, the sphere which is the boundary of the ball, the vector on this sphere, and you take the Gauss map, for you it is in the Gauss map, for each vector you take the parallel one going from 0, okay? And the Gauss map gives you a map from the sphere to the sphere, homology to homology of the sphere, so it is multiplication by an integer, which is your index. So you know very well that you need a manifold. If you have a singular variety, you cannot do the process. So you cannot compute an index. You need to be in a manifold. So if you have a point here, for example, thanks a lot to Alberto who gave me this nice. I can broke. No problem, no problem. Okay. Ah, but blue is not blue. Blue is not good. Because blue and blue. So, fortunately, Alberto gave me also a red one. No, that's bon. So, if you take a vector field which is tangent to your stratum, you can compute the index along the stratum. And then you can also extend your vector field in the ambient space, okay? And you will have another index. And you can extend, for example, you extend like this. But you see on my picture that the index along the stratum is different of the index in the ambient. Here is +1, here is, it will be -1. And you don't want this. So you want the index of your vector field in a singular point along the stratum which contains this point is equal to the index of your vector field at the point in the ambient manifold. You want this. If you have this, you will be able to work. Okay? And also, your vector field should be radial, going outwards of a singular point. For example, if I have a pitched torus, if I take the vector field, which is like this, tangent to the parallel, with a singular point here, your vector field, in fact, you can think that the vector field which is in R3 and which is going like this, so the index is 0. Your vector field is entering and going outside, entering and going outside the tube. Like, you forgot this, if you are in the torus, there is no singularity. Index is 0. If you compute Euler characteristic of the torus, it's easy. I let you make the computation with identification of this, with this. Okay? This gives you a sausage. And identification of this point with this point, which gives the pitched torus. And the Euler characteristic, if you compute, so Poincaré is false, is not true on this example. And Marianne Schwartz said, why? Because you took here, for a singular point, your vector field should be radial. What does it mean, radial? It means that your vector field should be going outside of your ball, like that. Okay? And then you have to extend. How do you do this? Very easy. So here is perpendicular. So you make a small inclination, bigger inclination, till you are tangent here. And you make the symmetric. So you have a vector field without any singularity, other singularity. There is only one. And here, as your vector field is going outside the ball, is radial, index is 1. So with this example, okay, point carrier is 2. So all the idea of Marie and Schwartz was to construct, for example, in such a case, if you have here something like that, it will be like this, sorry. Okay, so she will start with a vector field radial. So in every isolated stratum of dimension 0, it is radial, index plus 1. Then I extend the vector field, which is radial here. So it is now going like that. And you extend on the one-dimensional strata with isolated singular point. And then you extend with a method by Marie and Schwartz, which is very nice, using Whitney conditions A and B. I have no time to give into details, but using condition A and B, you can extend your vector field on a parallel by condition A and a transverse, which is 0 along the stratum by condition B. So we'll obtain a vector field which will be like that, going outwards a tubular neighborhood of your stratum. Okay, outside. Here it is going inside. So using Poincaré theorem with boundary, you can prove that you have Poincaré theorem for singular varieties. The problem, and I will finish with this, is that this is very complicated because using Whitney stratification is very complicated for two reasons. The first reason is that you see that you extend your vector field inside the ball, but you extend also your vector field inside the tubular neighborhood of the stratum. So there are some zones where you have vector fields arriving from the ball, from the stratum, and here there will only two stratum. But after that you will have more stratum. So how do you combine? How to combine all these vector fields in order to have a global vector field everywhere defined out of singular points, clearly. Okay? So this is first problem in Marie and Schwartz. She worked a lot on this, very, very, my God. She wrote a book on the question. And the other problem, it is a little different. I will do here, and I will finish with this problem. If you have a one-dimensional stratum like this, and a zero-dimensional stratum like this, okay? If you take a radial vector field going outside of the ball, it will be like that. The radial vector field is like that. So the radial vector field is not at all tangent to the one-dimensional stratum, as I wanted to be here, tangent to the one-dimensional stratum. So it is not at all tangent. So what you have to do, it's also a complicated trick. You have to take a called tapered neighborhood here. And in this tapered neighborhood, you will make an homothétie between this one and the projection of the space here. You will have a vector field which will be at the beginning like this, at the end like this, okay? And you imagine very well the homothétie between both, lambda times the first, 1 minus lambda times the second. So you see that there are complicated tricks. Now, I said already that I finished 3 times, but this is the real time to finish. Why in Lipschitz is easier, and this is the work we made together with Tadeusz Mostowski. Mostowski is the founder of Lipschitz stratifications, and with Paruzinski in the real case, Mostowski in the complex case. And so we can put the last one, and it is 1 minute. And so Lipschitz, what say Lipschitz? Lipschitz stratification says that you can extend taking care of all strata together, taking care of the distance to all strata together. So this problem I had here does not exist for Lipschitz stratification. It exists for Whitney stratification, but for Lipschitz stratification, so you can, for Lipschitz stratification is much more it's easier to do. And so we did this, and this is, I hope, very nice thing. Now, I did not speak of characteristic classes. You can do the same. This is, of course, in the real situation, but in the complex situation, you can do also the same for characteristic classes. So I hope you recognize all these guys. Also, sorry for Poincaré. Where is Poincaré? Here. So they let that one. They let that one. And Marianne Schwartz is here. And I have 3 observations to do. The first one is that only one woman in this figure. And oh, I have to take the 2. And only one guy with a computer. That's true, thank you. And one which is not the true one. So it's a tribute to human intelligence with all these guys. And I certify that my lecture is completely free of artificial intelligence. Nothing of artificial intelligence. And another example of human intelligence. Thank you. And happy birthday, Pepe. Thank you.
Any questions, comments?
So, since this is a celebration for Pepe's birthday, you overlooked the GSV index.
Ah, yeah, I did not say. I forgot. I wanted to say GSV. I wanted to say LVM. It's correct. I propose, instead of Euler characteristic, to say MDE. Mauricio, Descartes, Euler, in the same way that you did. And I wanted to say that, so thank you to say this, because I wanted to speak GSV, of course. So, and you know, Gomez-Mont is one of the GSV. This is the second, and this is the third.
No, but none of them saw that the alternating sum before. That is 20th century.
Yeah.
And it could not seem that things are equivalent if they are logically equivalent. In their context, there could be completely different.
That's true.
Okay.
But I think I am not sure, but you know also very well Poincaré books. I think that Poincaré, I've seen that Pichet torus is a counterexample for Poincaré of. Is it true? Do you know? Poincaré has seen that the Pichet torus, which was, is a counterexample for, as I no, it doesn't speak of this. Okay.
Okay, so let's thank the speaker again.
Oui. Je ne sais pas comment ça date. Le journal de l'instruction publique que je trouvais sur le site de la bibliothèque.